Hi everybody. So in this lesson we're going to be looking at chemical analysis, and we're going to be looking into chromatography, the testing of ions, gases, as well as the instruments that we might use to do these tests. So let's start at looking at pure substances and chromatography. So a pure substance is a single type of substance. Okay? That can be an element or it can be a compound. But it is only one type of that element or compound in a solution or in a in a container. That's a pure substance. So you can have pure water. Okay, it's called distilled water. It might be hydrogen and oxygen, but it is just H2O molecules. You could also have pure gold. Pure gold is a single type of element in that case, gold atoms. Okay, both of them, distilled water and gold, can be considered pure substances. So a lot of the times these pure substances are going to have specific melting and boiling points. These we call fixed points, and we can usually separate them by differentiating these melting and boiling points, in which case some will either melt while the other stays solid, or what can happen is the one will evaporate while the other one stays as a liquid. Thus we can separate them like this. Another way of doing this though, and separating mixtures of pure substances, is through chromatography. So chromatography can be used to separate amino acids, which are usually going to be colorless, but show when we spray an agent on them. Okay, I'll show you an example later of that. Basically how chromatography works is it's made up of a mobile phase and a stationary phase. The stationary phase we refer to is the chromatography paper. The mobile phase is going to be the solvent that is going to move up the chromatography paper. The solvent will then take our samples and move them up the stationary phase with the solvent. So here's an example of chromatography. As you can see here, our stationary phase would be our chromatography paper. It would be set up in this way. Firstly, we have to draw a baseline. It's important that this baseline is drawn in pencil. A lot of tests will draw it in pen and then ask you what is wrong with this experiment. If it is done in pen, the pen is then going to contaminate our samples, as the pen will also rise up the stationary phase or the chromatography paper. So we have to do it in pencil. The next thing that we have to take note of is how deep in the solvent we put our chromatography paper. Another thing tests will do is they will put the solvent well above the baseline and say, what is wrong with this? You would have to then say the solvent has to be below the baseline so that the samples don't disperse into the solvent. We don't want these samples to go into the solvent. We want the solvent to carry them up the chromatography paper. So we're going to place our samples onto the baseline. Usually what will happen is we are going to have two known samples and one unknown sample, which will be the mixture. The two known samples will be either a known mixture or pure substances. Once the solvent has gone up the chromatography paper, once the mobile phase has moved up the stationary phase, it is going to reach a certain height, which we can then mark with a pencil. That's important. Then what we will do is we're going to look at the separation of substances in our mixtures for each sample. And then we can see, well, in this sample, it's going to be made up of sample C, it's made up of sample B, and it's also made up of an unknown sample. And this is depending on how high the samples traveled up the chromatography paper. Now this is where it becomes specific about how chromatography can be used to identify pure substances. Every substance will have a certain attraction to the chromatography paper. This will either make it run a lot quicker and higher than the other samples, or it will have a harder time moving up and move slower and be at the bottom. Okay, so what's going to happen is we can measure how far the sample moved and how far the solvent has moved. This is going to create a ratio that we can document for that specific substance, and all other chromatography experiments for that substance will have the same ratio regardless of how long you left it in for, regardless of temperature, although temperature should also be kept the same, and regardless for how high the solvent went, because this ratio of solvent distance to sample distance will be the same. Here we can see an actual real life example of it, and you can see how the sample has spread up the chromatography paper. So this value that I was talking about is called the RT value. The RT value is going to be the distance moved by the substance divided by the distance moved by the solvent. And the temperature must in fact be kept the same as the original. If it is warmer, then it is going to move faster, or it can move through the chromatography paper a bit more than if it was colder, let's say. So temperature must be kept the same as the database. The database is going to have a set temperature that all of its tests were carried out at, and you must replicate that temperature. But the time that you leave it in for and the quantity of the sample does not matter in this case, which means that this chromatography can be very reliable to identify what these mixtures are made up of. I remember in university what we used to use chromatography paper for is to separate chlorophyll. There's different types of chlorophyll. It's chlorophyll A and chlorophyll B, and each one is going to move up the chromatography paper at different distances. This allows us to also isolate a certain sample of a pure substance. So now we're going to be looking at the tests for different gases that are produced during chemical reactions. The first is hydrogen. I think it is the most famous one because we all know it as the squeaky pop test. If hydrogen is present in a chemical reaction or in a test tube, we light a splint and we bring it towards the test tube. Hydrogen is very flammable, and therefore it's going to make a squeaky pop sound. When it comes to oxygen, oxygen is going to relight a glowing splint, because oxygen as well is quite flammable but not as reactive as hydrogen, so it is going to give life to a burning splinter. It's going to make that flame increase in size. The next is carbon dioxide. What we do with carbon dioxide is use lime water. So if you bubble the gases created by a chemical reaction through lime water, it is going to turn cloudy as it reacts with the lime water. And finally, when we do a test for chlorine gas is extremely toxic and will kill you. So we have to be very careful when testing for chlorine gas. What can happen is chlorine gas has a certain color, it has a yellowy color. But if small enough amounts are made, then we can't tell. So we have to use litmus paper. And what we do is we take damp litmus paper and we expose it to the gas, and it is going to bleach it and turn it white. Now, why do we use damp paper? It's because it allows the liquid on the litmus paper to react with the chlorine, whereas the dry litmus paper wouldn't react on its own. Now, when we start looking at testing for ions, we're going to begin with positive ions. So your positive ions are obviously your metals. Now your metals, when we burn them, are going to produce different colored flames, which is really cool. So if we burn lithium, it's going to produce this red colored flame. Sodium is going to produce a yellow flame, potassium a purple flame, calcium an orange one, and copper a green flame. And yeah, this is the only way to test for these positive ions. It's the most effective way. You're just going to burn little samples and see what color the flame is. If it is a mixed substance, you're going to get mixed results. So I guess this is only for pure substances. Now the test for negative ions isn't as cool, unfortunately. So first we have the test for carbonates. Carbonates plus a dilute acid will produce carbon dioxide. The test for chloride, bromide and iodide, or your halides, we're going to add dilute nitric acid and then silver nitrate solution, and a colored precipitate will form, so a solid will form that is colored. Okay. Iodide ions, I minus, gives a yellow precipitate, bromide ions give a creamy precipitate, and chloride gives a white precipitate. So the color of that precipitate is going to get darker the lower down that period or that group you're going to go. Down the periods in that group. Okay. So the test for sulfate ions is that we add dilute hydrochloric acid followed by barium chloride, which will give a white precipitate. So instead of doing the squeaky pops and all of that, what we can do is use instrumental analysis. So there are machines that are designed to do these experiments for us. Now the advantages is that it's a lot more accurate and sensitive than just the human eye or some cloudy lime. It's a lot quicker, and you only need very small samples to analyze this, whereas for us we would need quite a lot more. Okay. Some of the disadvantages of the modern equipment though is that it's very expensive. It requires training to use, so not anyone can use it. Like, we can do a lot of these experiments in school, but if we use the equipment, we're going to need training to do it, and very expensive equipment at that, and requires data from a known substance to compare its results to. If we don't have that data, the machine won't know, but we will. So advantages and disadvantages, pros and cons to it. The flame emission spectroscopy is exactly that. So when we were testing for positive ions, we lit a flame. Now there's a machine that will be able to burn your metal sample, and it will be able to identify what that metal sample is made of depending on the flame that it emits. Because as that substance gets heated up, its electrons are going to jump to another energy level, and as it releases that energy, okay, and goes back down, it's going to emit light. And that light radiation can then be picked up by the machine's special cameras and identified as what element we are talking about. Okay, so a bit of a weird lesson. I guess this stuff is just something, unfortunately, you're going to have to go over a couple times. Try and understand it, but it is just memory based, really. But I'm sure you'll be okay. So my name's Cameron, and I'll see you in the next lesson.